Hello everyone. Today I will be explaining about experiment 6 of digital signal processing lab. In this experiment we will be learning about filter design using pole zero placement method. So to design a suitable filter to remove the baseline matter from the given noisy PPG data using the pole zero placement method. This is the aim of our experiment. And pole zero placement method, how we will use this? This method is used for designing the frequency response of the narrowband filters such as low pass, high pass, band pass, digital resonators, notch filters and comb filter. So the general transfer function is of any filter is h of z is equals to g times the product of k equals to 1 times z minus zk by product of z minus pk. Here zk is number of zeros and pk are the number of poles and g is known as gain of the filter. So basically we are taking m zeros and n poles transfer function. And what are the rules for placing poles and zeros to design a filter? Rules are: first, the location of poles and zeros affect the frequencies from the system. So zeros on the unit circle at specified frequency reduces the magnetic frequency that responds or that frequency. So if we don't want any particular frequency, we will keep a zero near that frequency. Similarly, if we want the poles on the unit circle at specified frequency magnifies the magnetic response of the at that frequency. So if we want any particular frequency, so we keep a pole near it so that the frequency gets magnified. Basically the magnitude response of that frequency gets magnified. So what are the constraints on pole zero placement method? Now there are certain conditions we need to follow while placing pole zero placement method. They are: place poles inside the unit circle for stability, and zeros can be placed at any location in the Z-plane. So we can place zeros at any location in the Z-plane, but the poles must strictly be inside a unit circle. And when using complex poles and zeros, we need to work with conjugate poles. That means if we take a complex pole, then we need to include its conjugate poles also, because it results in real coefficients for our difference equation. So in this lab we'll be doing questions. Two questions. First one is: remove the baseline matter having the cutoff frequency of 0.4 Hz from the given unclean PPG data of 10 seconds using a suitable filter designed using pole zero placement method. So the sampling frequency is 80 Hz. Now we need to remove a 0.4 Hz baseline frequency from the PPG frequency range of 0.5 to 5 Hz. So we'll be using a low pass filter with cutoff frequency of 0.4 Hz. So the result transfer function would be g into 1 minus z power minus 1 by 1 minus r into z power minus 1. That is, we're keeping the 0 at the 0 on positive axis and we are keeping the pole near to it. So by applying inverse Z transform, we will be getting the difference equation as y of n is equals to r into y of n minus 1 plus g times x of n minus x of n minus 1, where g is the gain. So on calculating, we get the gain is 1 plus r by 2 and r is nothing but 1 minus pi by 100. So here is the code. First we are taking 800 samples in x, then we are considering another variable y. So we are implementing the equation we have learned earlier, that is y of I equals to r into y of I minus r into x of I minus x of I minus 1 plus g times y of I minus 1. So where g is 1 plus r by 2. So by substituting the values we will get this, and now we are printing x of I and y of I. So as you can see in this figure, this is the original signal with baseline component, and this is the final signal after removing the baseline component. So here we have removed the baseline component of 0.4 Hz, and this is the filtered output. Now in the second question, we need to synthesize the baseline components of 0.1 Hz, 0.2 Hz and 0.5 Hz, and we need to add it to clean PPG signal. Now again by filtering we need to remove those baseline components, and we need to find the error between the output we got through filter and the original clean PPG signal, and we need to measure the errors using mean square error, root mean square error and SNR. So these are the form. This is the error. Error is nothing but input PPG minus filtered output. So mean square error is nothing but 1 by n times summation of error square. Root mean square is the root of mean square error, and SNR is 10 times log input PPG square by error square. So we'll be implementing these three values now. So as you can see, first we have calculated the three components, point 1, point 2, point 25, and we are adding these three to BFI. So the final signal IFI is nothing but x of I plus 0.25 times BFI. BFI is nothing but the baseline signal which we have created. Again we are filtering it. We are filtering it through the previous equation which we have learned, and now we are plotting the original signal. Next the signal after adding the baseline component, and the third is the filtered signal. So as you can see here, we have printed three values. The first one is the original clean signal. Now the red line is the signal with which we have added the baseline drift. So this is the signal after adding the baseline drift. And the third one is the filtered signal. So in the next code, we will be calculating the error between this original signal and the filtered signal after adding the baseline drift. So as you can see here, again the same. Now we are calculating the baseline drift. We are adding it to the original signal, and that is y5. Now we are declaring a new variable error. Error is nothing but the original signal minus the filtered output f of 0, where the filtered one is this one. F of I is nothing but the filter coefficient which we have learned earlier. So we will be calculating our mean square error, root mean square error, and SNR. Our mean square error is sum of the errors by 800. Error sum is nothing but here the error square. Root mean square is square root of MSA, and SNR is 10 times log of energy of the signal. Energy of the signal is nothing but x of I square by error sum, which is nothing but error square. So we'll be printing these three values now. So as you can see here, we have calculated three values. The mean square error is 0.02, the root mean square error is 0.14, and the SNR is 16.13. So we have finally calculated the filtered signal, and the error of the filtered signal with respect to original signal by using three mean square error, root mean square error, and SNR. So thank you.